Hello everyone, I'm Tiziano Matteis from Spatial Lab, ATH, Zurich. And today I'm going to present you FBLAS, our work on a streaming linear algebra library for FPGAs. In the last few years, the end of the nano-scaling and the slowdown of Moore's laws have driven the computing community to investigate new types of computer hardware, able to overcome control and data movement overheads that are typical of loaded store architectures. From the one side, domain-specific architectures are often proposed to accelerate specific application domains. They are able to achieve high efficiency by tailoring the architecture to the domain needs. Examples of domain-specific architectures are Google TPU, Algebra Waverscale Engine, and Habana chips for inference and training. On the other hand, special computing devices are gaining attention as a way to allow rapid prototyping of application-specific circuits that are driven by the data movement itself. An implementation of this paradigm is constituted by FPGAs, such as the devices offered by Intel, Xilinx, and many other vendors. In this work, we focus on FPGA. In particular, modern FPGAs are an interesting platform also for scientific and HPC application. Indeed, they are equipped with native floating point unit, high bandwidth memory, and high-speed network connection. Recently, the diffusion of high-level synthesis tools is also facilitating the life of programmers. However, despite this, the development cycle of an FPGA program is still a long and tedious task. Optimizing for FPGAs is more challenging than doing it for load and store architectures such as CPU and GPU, since the space utilization is another key metric to consider together with performance. This led to a space-time tradeoff, which must be considered by the programmer. Finally, the situation is further hampered by the lack of public available hardware libraries or reusable components, and any times the programmer has to implement everything from scratch. In this paper, we proposed FBLAS, a flexible and customizable implementation of the BLAS routines for FPGAs. Our objective is twofold. First of all, we want to enable the rapid development of numerical applications that target spatial architecture, giving to the lectureless programmer access to a set of customizable routines that can be reused, composed, and integrated with other program logic. As a byproduct of this, we want to provide insight on the development of hardware libraries using HLS tools. This because we believe that the challenges that we faced and the solution that we proposed can be applicable also to other domains. Let's have a look on how FBLAS is organized. Now, currently, FBLAS targets Intel devices, and it's comprised of two main components. HLS modules are independent computational entities that implement a library functions. In our case, they implement BLAS routines. They could be seen as specialized hardware operators. They have been implemented with optimization in order to exploit the hardware resources of the FPGAs, and they are equipped with streaming interface that will enable to compose them and exploit on-chip resources. Then we have a host layer which provides a full compliant BLAS API to allow the offloading of part of the computation to the FPGAs. Therefore, the user has two ways of interacting with the library. She can invoke routine from a host program, or she can incorporate modules into her own HLS program. To produce the HLS modules that are required by both this way of interacting with the library, we provide also a template-based code generator that takes an input a JSON description of the routine that are needed by the programmer and produce a set of OpenCL kernels that are ready to be synthesized. For what concerns modules, we implemented them with key HLS transformation in order to exploit the spatial parallelism and the fast on-chip memory of FPGAs. So writing HLS programs revolves around designing deeply pipelined circuits that are expressed using nested loop. To achieve high efficiency, it's crucial that these loops have an initiation interval of 1, meaning that a new loop iteration is started on every clock cycle. To allow this, we resolve loop carrier dependency and hardware resource contention by applying transformation such as iteration space transposition, loop stream mining, and accumulation interleaving. Parallelism on FPGA is achieved by replicating computing units. We achieve this by unrolling loop nest according to a desired vectorization with a parameter of the replication factor. Then we used also loop tiling, which is a well-known code optimization used to increase both spatial and temporal locality in computation. In FBLAS, tiling is used for level 2 and level 3 routines, where there is an opportunity for data reuse. Finally, for GEM, we offer a systolic array implementation that allows the module to use a vast portion of the entire chip resources. All these optimizations are offered for free to the user, but they are also configurable to allow the user to specialize the module according to the desired performance or utilization requirements. Now let's consider replication and tiling and see what are the effects of acting on these two optimizations. For example, the user may want to increase the vectorization width in order to reduce the completion time. But this, on the other hand, will increase also the spatial resources because we will need more resources to carry on the computation. And similarly, if we increase the tile size, from one hand we will reduce the layer complexity of the computation, but from the other hand we will increase also the use of on-chip memory because we will need more space to accommodate the data. So this is an example of the Spacetime tradeoff, that is a compromise between resource consumption and the performance. And this because differently than CPU and GPU with spatial devices, time but also space are the two key metrics to consider in optimizing the code. So this space-time trade-off must be understood to optimize the performance and or the resource usage of the resulting design. Now in FBLAS, HLS modules implement hardware numerical routines by means of fully pipelined nested loop. So here I'm showing you the pseudocode of the dot module, where we receive the data from two channels, channel X and Y, and we produce the results on channel res. So in the example, we can see that there is an innermost loop which performs the actual processing. And generally, this is a rolled loop, and it's a rolled according to the vectorization width W. And this is synthesized as a circuit that implements the desired computation. The outermost loop are derived from loop unrolling, as the example that I'm showing, or generally also from tiling for level 2 and level 3 routines, and they are the schedule in which the computation is performed. Therefore, the vectorization width and the tile sizes are the two knobs on which the programmer can act in order to change the module performance and use of the resources. To capture the space-time trade-off, we introduce a model to analyze the relation between the parallelism, the resource consumption, and the performance of an FPGA design. In particular, we consider to model the circuits by using the work and depth model. Now, the cost of an algorithm in the work and depth model is defined by the total number of operations that are performed in a computation, the work, and the depth, that is the length of the critical path. Now we adapted this concept also to synthesizer circuits. Let's take again the dot module, and as we said, the innermost loop is synthesized as a circuit. Now in this case, this can be implemented efficiently by using a tree-like structure, like the one shown in figure. Here we are using a vectorization width equal to 4. The leaves we have the input elements, so the elements of I, X and Y, and at the root we have the final result. Now from here we can derive the circuit work, which in this case is double the vectorization width, so the number of nodes in the tree. And similarly we can derive the circuit depth, which is the logarithmic function of the vectorization width. Here in the formula, LIA and LM are respectively the latency of the addition and multiplication operation. Now we can combine this information together with the fact that we know that the module is pipelined. So in a pipeline module, the execution time can be computed by considering the latency of the module, L, plus the initiation interval, 1 in our case, times the number of input elements. Now we can substitute in this formula the circuit depth and the number of elements, which is given by n, the length of the vectors, divided by w, the vectorization width. Now this is offered to the user, which can understand how the space-time trade-off changes as long as she changes the vectorization width, for example. So, for example, if we increase the vectorization width w, we will linearly increase the circuit work, so the resources that are used by the circuit. We will linearly decrease the execution time and only logarithmically increase the circuit depth, the latency. And this is for the single module, but of course in real application we will have multiple modules that are executed together. Therefore, the programmer can use these modules to understand the optimal vectorization width, that is, how to dimension the circuit so that the module is not a bottleneck while not over-provisioning the resources. So you can find more details about this in the paper. Another important thing that I want to discuss with you is the module composition. Now, as I said at the beginning, these modules have streaming interfaces that enable the communication through on-chip memory rather than through off-chip DRAM. Let me explain this with an example. Suppose that we want to compute the following results. Here A is an n by n matrix and u, v, x, and y are vectors of n elements. Now to compute this we need two BLAS calls, one for the outer product, which is computed by Gear, and the other one for the matrix vector multiplication. In a classical, let's say, setup, we will start the outer product, which will save the result on the DRAM, and only after that we will start executing the matrix vector multiplication. Now with a streaming implementation, we can let the outer product stream the result directly to the matrix vector multiplication. So these are two advantages. First of all, we reduce the I/O complexity of our algorithm. And secondly, we also allow the pipelined parallel model execution because the two routines are able to execute in parallel. To reason about this string composition, we introduced this concept of module-directed acyclic graph. So the computation are expressed by this DAG where the source and the sink nodes are interfaces to and from the DRAM, and the inner modules represent modules that perform the computation. In our case, they will be FBLAS modules. Now, an MDAG is valid if it expresses a composition that will terminate and all the edges are valid, meaning that the number and the order of elements that are produced on an edge is identical to the number of and order of elements that are consumed. Let me show a couple of examples. So, a possible way of composing modules is by using multi-trees composition. So, a multi-tree is a graph where only a single path exists between any pair of nodes. A multi-tree module composition with valid edges is always valid. Consider, for example, these that are computation derived from the extended BLAS. So, in AXPDOT, we have a computation that involves different vectors of size n. So this can be implemented by using three BLAS calls, one copy, one AXP, and one dot product. This will give us a certain I/O complexity if it is implemented in a standard way. Now, with the streaming implementation, we can allow the AXP module to stream the data directly to the dot product. So this will reduce the I/O complexity, is less than half of the previous case, and also we have that the two modules run in parallel, therefore further contributing in the reduction of the execution time. In BCG, which is a computation used in biconjugate gradient, we have operations that involve a matrix of n by n elements and p, q, s, and r that are vectors of n elements. So this will require two matrix vector multiplication, therefore to read the matrix two times. But we can use also in this case a streaming composition. We can read A only once, assuming that the two GenV modules accept the data streamed in the same way. Now this is an important concept that we apply in the development of BLAS. So we have modules that accept the data streamed in different way, and these are offered as different specialized modules. This favors the module composition, as in this case. Of course, also in this case, we are able to reduce the I/O complexity, so it's half of the previous case, and again the two GenV are able to run in parallel. For more complicated graphs, invalid composition could occur, and this is mainly due to the fact that multiple paths can exist between a given pair of nodes. Now in the paper we discussed the possible solution to this. One of them could be to split the graph in multiple valid components, like we did in the GenVer examples here shown on the right. You can find more details about this in the paper. For evaluation, we consider two devices. One is based on the Intel Area 10 chip and the other one on the Stratix 10 chip, which is the Intel flagship FPGA. So we consider the single module evaluation. In particular, we want to see how they will scale when we change the vectorization width and tiling. Now we consider the DOT, the GenV, and the GEM modules as representatives of level 1, 2, and 3 routines. For DOT and GenV, the data is generated directly on chip in order to not be bottlenecked by the DRAM. So here I'm showing you the result for the DOT module. So on the x-axis is reported the vectorization width, on the y-axis is reported the performance in logarithmic scale. Now for each of the vectorization widths you will see 4 different bars. The first two refers to the area chip, single and double precision, and the other two for Stratix, single and double precision. On the top of each bar is reported as a tick dash the expected performance computed by considering the used resources and the frequency, the final frequency of the circuit. So in general, the Stratix 10 is able to achieve higher performance with respect to the area chip. This because generally the synthesis frequency of the circuits for Stratix is higher with respect to the circuit for the area 10. Apart from this, in general, as long as we increase the vectorization width, the performance increase accordingly. For 256 vectorization width, we have the results only for the single precision version. This because these devices have single precision hardened floating point unit. Therefore, operation single precision are directly implemented on hardware. When we use double precision, the operation must be emulated in hardware, and this usually requires 4 times the resources that are needed for the equivalent single precision module. This is because we were not able to scale the double precision routines up to 256 vectorization width. For GenV, we have similar results, and again the performance results increase accordingly to the vectorization width. For GEM, we wanted to show the highest obtainable performance, and therefore we considered the largest systolic array that we were able to synthesize without having the compiler failing the place and route phases. This is the reason why we have different array sizes depending on the device and the precision that is used. So once we fixed the systolic array size, we let the memory tile size vary in order to understand how the resulting circuits behave with an increasing memory tile sizes. So as you can see in the plot here, as long as we increase the memory tile sizes, the achieved performance are approaching the expected ones till we reach up to almost 1.3 teraops for single precision on the Stratix 10 device. As before, for double precision, we are able to obtain lower performances because we need more resources to compile the result, the circuit. In general, a historical implementation allowed us to let the design scale to use a vast portion of the chip, that is up to 86% of VRAM and 73% of the available DSPs. The paper we discussed also results on the streaming composition, where we evaluated the speed up with respect to the DRAM implementation, and the achieved results are in line with our expectations. And also we compared the FPGA with the CPU. Here are shown the result of the speed up of the FPGA over the CPU implementation. So due to the lack of proper hardware units, compute-intensive routines such as the matrix multiplication that operates with double precision numbers do not benefit from the execution on the FPGAs. So, given all of this, we therefore recommend to use FBLAS in scenarios that are a good fit for the FPGA architecture, that are programs where we have multiple modules that are composed in streaming components, and therefore we can exploit streaming interfaces, and or deeply pipelined circuits with a high degree of spatial parallelism, such as the gem in single precision. To conclude, in this paper we presented FBLAS, the first public available HLS implementation of BLAS routines. In the paper we proposed a method of spatial library design where configurable components with flexible interfaces are offered to the user. These components can be plugged into existing designs to exploit streaming compositions. FBLAS modules are offered with K-transformation that exploit the hardware characteristics of spatial devices, and they are designed such that the resource usage and the performance is tunable according to a model of their space-time trade-off, allowing them to be specialized to the user application needs. Finally, we have seen how the streaming interface exposed by FBLAS routines can be used to compose multiple modules and let them communicate through on-chip resources. This will lower the I/O complexity and will allow the parallel execution of multiple modules. So while in this paper we focused on dense linear algebra computation, we believe that these can be key considerations also for the development of other spatial hardware libraries. FBLAS is released as an open source project and we hope to involve the community in its further development. This concludes my presentation, and now I will be happy to take your questions.